Let's look at work energy theorem, or in other words, the relationship between work and energy. We know from rectilinear motion or kinematics equation that v square minus u square is 2as, where v is the initial final velocity, u is the initial velocity, a is acceleration, and s is displacement. Now this can also be written as v square minus u square equals 2 times acceleration vector with the dot product of the displacement vector. A is acceleration, s is displacement, but when we represent them as dot product of the corresponding vectors, the angle between A acceleration and the displacement is, they are on the same line, so it's 0. So the dot product of A and D is nothing but magnitude of A times magnitude of D cos theta. Cos 0 is always 1. So you can represent the product of A and S as the dot product of the A vector and the S or the displacement vector. So now let's multiply both sides by mass by 2. So what happens to the left hand side of the equation? It becomes half mv square minus half mu square. We know that these two are the kinetic energies. So this is typically the difference between the final kinetic energy minus initial kinetic energy. The right hand side becomes half times m times 2 a vector dot d vector. Now these twos cancel out. We give m times a. We know that it is nothing but force. M times a is nothing but force. So the difference between these two is nothing but kinetic energy final minus kinetic energy initial. The difference in the kinetic energies. This equals m and a together give you the force vector dot d vector. So we know F dot D, when you apply a force, net force to an object and it gets displaced by a distance, then this is nothing but work. We represent it by W here. So work equals the change in kinetic energy. So the change in kinetic energy here is equal to the work done. So this gives a relationship between kinetic energies or energies and work. And this is the motivation for the work energy theorem.